Hi, Dr. Sellens. Here in the lab, I figured I'd just make you a quick video so you could a little better understand. It's just easier for me to talk about what I've done and what I'm doing here about reading these current signals utilizing the skills you have taught me on the Arduino. So, I got it working. Just give a quick rundown. First, purchased the wing shield here that has the terminal screw style connections. So I've got my 5 op amps, which are the Texas Instruments OPs 07 unity gain voltage followers, and I've got those hooked up to my 5 pull down resistors that basically give me a full scale 3.3 volts at 50 microamps. And that, of course, got some more wiring all done in there, but it is all soldered and working. And so off this thing I have 5 lead wires that go to the input side of the op amps, which come down across here. They come through my vacuum feed through, and this would be, now we're in vacuum space. I've got these pins where the wires come off, they come up, and each one comes nicely to my 4 tantalum detectors, and I've got 1 pin that goes into the back of the copper block. So those are my 5 signals, and you can see the tantalum is electrically isolated, in fact, because I've got washer and then a tube and then another washer, which are all made of aluminum. So they are, each one is independently hovering in space, and as well as this copper block is also hovering in space, so it's not touching the chassis. The only path for electrical current to flow is from the copper to this stainless joint, which is acting as my water in and out, coming down to this ceramic brake. Now the ceramic brake, if I can measure, it's rated for 15,000 volts. If I can just measure the impedance, I've got about 20 mega ohms across. So I know I'm not losing much of the signal through these brakes. So that being said, I'm able to simulate and actually try to record some of these microcurrent signals by, first of all, having the Arduino plugged into the wall so I can get a clean 5.1 volts coming off just to a mega ohm resistor in series, which should give me about 5 microamps theoretically. So to test that, just come here. I'm going to throw it on one of my detectors, like so. And then on my printout, all I do is I read 100 times and take an average. And you can see basically current 2 is reading about 4.6. I'm just printing out with time and my 5 current measurements. So that's about the half a microamp, is about the best I've been able to do in refining these signals. I don't know, there's not much loss between the two, but even because the distance is not that far, but even the unity gain voltage followers are about plus or minus 1 millivolt error on them, as they do try to regulate the signal coming in. However, I just am, for our purposes at the lab, the half microamp is more than enough satisfaction for our measurement purposes. So that being said, I could just quickly show, I probe this area here. Computer is turned off. Oh, sorry about that. Probe that current there. You can see current signal 1 is reading as well the same, about 4.6. So what I do want to do is, I'm happy with that. I've tested for a few different input currents all the way from about 1 down to up to 40 microamps. And like I said, I've just from my own work here, I'm getting about accuracy to half a microamp, which I probably just need better fine-tuned electronics to get anything better than that. So what I am going to do, though, is, as you can see, this copper block, it has 2 cartridge heaters going into the back, which are powered by AC current. And they feature a nickel chromium sort of coil in there that it acts as just a direct resistor to heat this block. So when I do heat and apply full current to the cartridge heaters, with about a couple amps of AC, I am getting quite a variation in the current that I'm then trying to read off this copper block. It's not critical to our experiments here because we do just want to heat up this block, heat up our test material that's going to go on this face, and then turn on the proton beam, which would be entering in this direction here. So once the heaters are relatively stable and they don't have that much power and we're up to our temperature, then again I don't see much fluctuation in my readings, which is fine. And then we can just simply adjust these up and down, left and right, and create a smaller or larger window where we can essentially monitor this beam's position in 2D space. I can sweep it left and right and I can bring it up and down just by reading the current signals that'll be hitting the superconductive tantalum plates. We also use tantalum because it's a very heavy metal and it's not going to become radioactive when our particular beam does decide to hit it, which is just protons of hydrogen and helium, 8 mega electron volts and 12 respectively. What I am going to test and include in the report is the only way, and things I might be concerned about, is the water cooling coming in is not deionized. So as my full head of 30 psi water comes in through this 3/4 inch pipe, comes in and out, I may have some electrical loss even though there are the ceramic breaks. So that's going to be something I'm going to test for different pressures and flow rates, and you'll like this. I can do this, of course, from my Omega flow rate transducer, which will basically tell me what my output is, send a signal to my PID controller here, which goes to this proportioning solenoid valve, which takes a 4 to 20 milliamp control signal. So I'll be able to adjust, obviously, my perceived value from my set value, and then be able to regulate some flow, and also then communicate with another thermocouple back here to get some sort of cooling control system in place. So I'm hoping whatever this cooling is at maximum pressure, whatever loss I do have electrically, I can just put that back into the Arduino and then essentially give an inflated version of what the actual current would be hitting the block, even though the Arduino might be reading, who knows, 20 to 15% lower than actual value. Anyway, thanks for listening. This is our setup here. I hope you enjoy this video. It's just a little something for the visualization aspect of it, and thanks for listening.